Okay, so yeah, today is the last lecture, because next time we're going to have a review, and then after that we have the final exam on Friday. So the last thing I want to discuss in this class is this notion of compact metric spaces. We already discussed this last time, but so yeah, recall from last time. The idea is today our topological space today is going to be a metric space. We say that for a bounded set, so you have a subset of some, let me abuse this notation. I have a subset of a metric space. For such A, we defined the diameter of A as this supremum. So you take all possible distances between two elements in A, and then you take the supremum of that set. And that's the diameter of A. And of course, you can only define this diameter when this supremum exists. And for this to exist, you need to be sure this set is not empty. That's going to be guaranteed if A is not empty. And then you also need to ask this set to have an upper bound, So that's what we call the bounded set. Some set for which this set of all possible distances has an upper bound. Then you can define the supremum, that's the diameter. And of course, it's kind of doing what's supposed to do, right? It's like, if this is your A, you will have some short distances, maybe. But then the diameter should be, well, not really this distance, because we're taking the supremum, and then maybe these 2 points don't lie in the set, but something like that, right? Okay, so the thing we want to prove today is we want to prove this theorem. So the Lebesgue number lemma. So this is a theorem for compact metric spaces. So I'll take XD to be a compact metric space. And I will take an open covering for this metric space, an arbitrary open covering. So let U be an open covering. For X. Of course, open with respect to the metric topology. Then the statement is, then there exists some positive number, delta. We always use delta for Lebesgue numbers, such that, so here's the property of delta. For every subset A inside of X, which I want to ask this A to be bounded and non-empty. For every A with the diameter smaller than delta, there is some open set in the open covering, some open set U in our calligraphic U that contains A. So what's kind of going on here is so maybe I want to emphasize this, compact metric space. So what's going on here is, this is telling us something like, we don't know what delta is, but it's telling you for any set that's not too big or too large, then that's going to be a subset of one of the elements in your covering. So in some sense, it's telling you your covering doesn't have two small sets. It's like sets they contain everything that's not too small. so that they themselves cannot be too small. I don't know how surprising this is, but we'll see an application later on. And of course, we can cook up examples where this is not true. It's very easy to construct examples. For example, maybe I should have mentioned this last time. Example in R, say, this is not true. For example, if you take maybe I need to think about this better before I claim this, but I'm quite sure if you take these open balls of radius 1 centered at integers, this is an open covering, and it will not have that property. Maybe we can think about that in office hours, but okay, so the fact that X is compact is going to be very important, and now we need to prove this theorem. Any questions before we prove the theorem? Okay, proof. I will start the proof here because I want to say something kind of naive before I actually go to the proof, because I will need this technicality. So the technicality is if U, the covering, happens to contain X, which is an open set on itself, then we're kind of done, right? Because independently of what A is, independently of this condition, everything will be contained in X. So the case where you, in case X happens to live in the open covering, that's kind of nonsense. You never want entire space in your coverings, but that could happen. Then any delta will work. Any delta would work. Because X contains everything independently of the diameter of whatever you have. So we can just assume that's not the case. So can assume, and actually should assume, that X is not in U. Okay, now how do we use this assumption? This is a clever proof. So this proof will use an idea that's, I don't know if anyone of us could reach to this idea in a finite amount of time. Probably if we have like 10 years to think about this, we'll come up with a proof. But if you give me like 2 hours, I don't know if I can come up with the proof, or at least the proof that I'm going to give for this theorem. So what's the idea here is, well, to begin with, we have an open covering of a compact space. So since X is compact, and this is the only place where I'm going to use this, well, not really. I'm going to use this 2 times, but since X is compact and U is an open cover, we know that we can just restrict ourselves to so finite subcover. It's an open covering. There are some finitely many. Let's call these guys U1, blah, blah, blah. UN, let's say, in U, that will cover X. So we're just safe with finitely many of these open sets. And the idea now is for each of these i's between 1 and n, so for each of these indices, I'm going to take the complement of U. So take Ci to be the complement of U. And it's closed, but most importantly, it's non-empty. So this is a closed, not important so far, non-empty set. So we have finitely many, And since Ci is non-empty, we have a continuous function taking the distance from a point x to Ci. So now we're going to define a function f out of x to the reals. And this function, what's going to do is, remember here, we have a well-defined continuous map taking little x to the distance from x to Ci. That's because Ci is non-empty. That's why I don't want my entire set x to be one of these UIs. So this is continuous. And these are going to be the building blocks of the proof, these functions that are continuous. This is what we discussed last time. I didn't prove this distance function is continuous. So let's take a function, let's define this function by, we're somehow going to take the distance of a point to Ci, but I'm going to consider all possible Ci's, and I'm going to average the distance, and that's going to be f of x. And this function is going to be continuous because it's a sum of continuous functions. So the upshot here will be x is a compact space, f is a continuous function. So it will attain a minimum and a maximum. We want to take the minimum, and that should be our delta. So at the end of the day, what we're going to take is delta to be the minimum of f of x. That's kind of the image of f. We need to be more precise about this, but that's essentially the idea now. So the first problem is we don't know if delta is going to be positive. So this function is taking non-negative values, but the minimum could be 0, right? Like x goes to x squared. So the first claim is f of x is always positive. So how do we prove this? Let's prove this. In fact, if you give me any little x in big X, which is the union of finitely many of these UIs, if I want to show f of x is positive, essentially I need to show that one of these guys is positive, right? Because then you're summing non-negative things. So if that's the case, we have that x lives in uj for some j between 1 and n, right? But now uj is open. Why am I doing this? Because I want to show the distance from x to Ci is positive. Ci is the complement of uj. When uj is open, you have something in an open set that needs to be separated from its complement. So how do we say that? Since uj is open, points in uj are going to be separated from the complement. Let's write that. Since uj is open, there exists some positive epsilon such that the ball centered at x of radius epsilon is inside uj. So what we're saying is, I don't really know what uj is. We know it's open. Here's our x. We know there's an open ball here. So here's our uj. And whatever else we have is the complement. So this is our epsilon, that radius. And whatever's outside, that's the complement. That's zj. But if the entire ball centered at x of radius epsilon is inside of uj, that means there is no stuff of distance smaller than epsilon from X that's in Zj. Right? So thus, for any element, let's call this Y in Zj, which is the complement, we know that Y cannot live in this ball because the ball is inside Uj, not the complement. We have the distance from X to Y bigger than or equal to epsilon. And remember, hence, the distance from X to Zj, which is defined as the infimum of all possible distances from X to Y, where Y lives in Zj. Epsilon is a lower bound for this set, that's what we're saying, so the infimum is going to be at least epsilon. And then we're essentially done. If this guy is positive, then of course f of x is going to be positive because we're just doing extra stuff involving non-negative numbers. So how do we write that? Maybe I'll need to continue in another whiteboard, but that's essentially the only thing we need to say. It's probably what's going on here. Okay. So let's finish the proof of claim 1. That situation, when we compute f of x, remember this is 1 over n. So let's take n here. This is the sum from 1 to n of these distances, Ci, which is at least one of them, because everything else is non-negative, which is bigger than epsilon, bigger than or equal to. And this means f of x is bigger than or equal to epsilon over n, which is definitely a positive number. And that's the end of the proof of claim 1. Okay. So why are we doing this? Only because we want to take the minimum of f, and we know we need that guy to be positive. So since f goes from x to, let's take the positive real now, the positive reals is continuous, and x is compact, we know from the extreme value theorem we proved last time, we know, so this is a very non-trivial theorem, there exists some delta, which is what I call f of x mean, right? Which is positive because f of anything is positive, such that delta is going to be smaller than or equal to f of x for every x in x. So that's delta, minimum of f of x, which exists because x is compact. Are we okay? Now claim 2, this delta works. So it does what's supposed to do in the theorem. So how do we prove it works? To prove this delta works, we need to take an open set, sorry. So to prove it works, we need to take some subset of x with diameter at most delta, or smaller than delta. And we want to find some u, want to show there exists something in the open covering that contains A. Right? So this guy will actually be one of the finitely many that we have. And we need to be very specific about how we prove that. So the proof here will depend on of course, this A is bounded, so that this makes sense and not empty. The proof will depend on just fixing a point of A. So fix your favorite point in A. Let's call this X star. So the first step of this proof is, for claim 2, step 1. We have this delta here. If you take, this is kind of independent of whatever else is going on here. This should be for any set with diameter at most delta and any point inside the set. If you take the ball at center X star and radius delta, then this should be inside your set A. Oh, well, the other way around. This should contain. So what are we saying here? Let's see if I have enough space. So what we're saying, to illustrate this, is we have our A, whatever it is. Remember, can be open somewhere. I have an X here, X star. This is the diameter. This is the diameter, which is at most delta. So what I'm saying here is delta is comprised of this portion and this portion, right? So what I'm saying now is, if instead of taking just this line, you take that line, maybe let's go blue. You take like this line here and append this little portion, and you take the entire ball around it, it should contain A. That's what they're saying. So the picture might be confusing. The proof is very easy. So the proof is very easy because if we take, why is this true? In fact, we'll try to prove it here so that we have the picture nearby. In fact, if we take some Y in A, so your Y is somewhere, then the distance from X star, maybe X star to Y, that's smaller than or equal to the diameter of A, because this guy is the supremum of all these distances, which is more than delta. That's what we're assuming. So that's all we need to say. That's exactly what we're claiming. If you take anything in A, then it lives here. So Y lives in this ball. That's all that's going on. And this is completely independent of everything. If you have a set of diameter smaller than something, you take any point in the set and take this ball with that something, then it's going to contain the set. Because diameter is smaller than that. Nothing too crazy. So step 1 is that. Step 2, this ball, this is kind of the important part, is inside one of these UIs. It's inside U. What notation do I want to use? Maybe let's, I don't want to fix an index now. This guy is contained in some of these open elements in the covering. And then if A is inside the ball and the ball is inside one of these guys, then we're done. So this is the last thing we need to prove. So here's the idea for this. Maybe let's start with the argument, and then I'll tell you what's going on in the picture. So we have all these distances. Maybe I will need more space. We have all these distances from X star to Ci, where I is something between 1 and n. So all these things that I'm adding up to get my f of x. So these distances, finitely many things, one of them is going to be the maximum here. So this is going to be the distance from X star to Cj for some j. Maybe I don't want to use j because I used it before. I want to use n. So take some m between 1 and n such that that distance is the maximum. So for this m, what we have is the following. When you compute f of x star, I'm trying to show that this is inside one of these guys. So when I compute f of x star, this guy is 1 over n, the sum over I of these distances, x star. That's the definition. But now each of these guys is smaller than or equal to the m guy that I just fixed. So I can just replace each of those by the corresponding Cm. But now this is independent of I. So this is just, I will get n of these guys, 1 over n. So this is just x star Cm. Now, why am I doing this? I want to show something about this ball here, centered at x star of radius delta. I have this distance, but this guy is always at least delta, because delta is the minimum. So what we're saying here is delta is smaller than or equal to the distance from x star to Cm. And now, what is that telling us? We know that our x star lives. So it's going to maximize the distance. Here's our x star again. Here's our Cm. Now I want to focus on the complement, Cm. We know that the distance is at least delta. So this is at least delta. So stuff that's a distance smaller than delta from x star cannot live in C. So let's write this. Hence, stuff that's a distance smaller than delta cannot live in C. And that says it's contained in U. So how do we prove this? If you want to prove this carefully, it's just by contradiction. So how do we prove this? Do I have an argument? I don't, but let's come up with one. So if the distance from x star to y is smaller than delta, so I'm taking something here, and y lives in Cm, in UM, sorry. Right, and y lives in Cm for a contradiction, then the distance from x star to Cm is going to be smaller than or equal to the distance from X star to Y, which is smaller than delta. And that's a contradiction. Okay. So what I'm doing is I'm taking any guy like here, that's your Y, and I'm proving it cannot live here. Because if it does, then this distance is going to be smaller than delta. That's not possible. And then we're done, right? Because step 1 and step 2, we have step 1, A is inside this ball here, Cm, which is no, we're not done. What's going on here? Right, sorry, that's the problem. It's delta, and this guy we're proving is inside some Um. And that's the end of the proof. Okay, any questions? So I think it's a nice proof, because sometimes with this class, one starts to get this feeling that I can prove all the theorems. I just need some time. I will be able to prove everything. And this is telling you, well, there's some stuff that's not so obvious, but still true. And I think that's good, because that's telling you that there's more topology. We need to, with enough time, we could learn very non-trivial stuff. So I wanted to include this proof today to show you, or to challenge you to maybe consider the option of taking more topology classes. Because there is a bunch of stuff that we are not covering. In particular, there's something called algebraic topology that, of course, we cannot cover in this class. It's completely unrelated to this, but uses very clever ideas coming from another areas to do stuff. Okay, any questions about the proof? So let's see a very cool application of this. And I like this application because it came up as a question a lot of time ago. So let's take two metric spaces, X with this distance and Y with its own distance, metric spaces. And let's take a function. Let's call it f, of course, from X to Y. I want to define what's a uniformly continuous function. So a function like this is uniformly continuous. Uniformly continuous if given epsilon, there exists some positive delta such that, so uniformly continuous means given epsilon, the delta that you take is independent of X. That's what it means. Such that f of the ball center at X of radius delta is going to be inside the given ball. F of X, radius epsilon, but that's for every X. And of course, balls here are taken with respect to the distance in X, and balls here are taken with respect to the distance in Y. That's the definition of uniformly continuous function. In other words, what we're saying here is, for every x1, x2. Maybe I can say it again with another color even. In other words, for every positive epsilon exists some positive delta such that if the distance from x1 to x2 in x is smaller than delta, then the distance in y from f of x1 to f of x2 is more than epsilon. And this is for every x1, x2. Are you familiar with this notion? It's like just saying, given epsilon, delta is independent of x. Okay, theorem. Uniformly, how do I call this? Uniform continuity theorem. That's how I would call it. Uniform theorem. So this is a theorem that you sometimes prove in analysis, but not really, and not usually, maybe. So let's take two metric spaces, and I want the first one to be compact. So let's write here. Let f going out of x dx to y dy be a continuous map. So what I'm saying here is I have two metric spaces and a function that's continuous when you consider the metric topologies. If x happens to be compact, then f is going to be uniformly continuous. So what we're saying is any continuous map going out of a compact space is uniformly continuous. Something I should have mentioned is, of course, any uniformly continuous function is continuous. What we're seeing here is if your domain is compact, the converse is also true. And this is very important in a bunch of different areas. Like, yeah, for example, differential equations, this is a very useful theorem to have. Okay, so of course, everything here. So I want to say two things. The first thing is you can prove this theorem without using the Lebesgue number theorem. But it involves some work. So maybe if you're bored, try to prove this without using the Lebesgue number theorem. Essentially, what you'll do is you will take an epsilon, and then for each x, you'll have a delta. And then for that collection of open balls, you should have a finite subcover of x, which is compact. And then maybe do something about that finite subcover. You can take like minimum delta or something and see if that works. That could be a very good idea. But not really. So what I'm trying to say is there's a not so easy proof, but that's independent of the Lebesgue number lemma. But using the Lebesgue number lemma, we can give a very short proof. So proof. So the idea here is, let's take some positive epsilon, because that's what we need to do, right? To show that f is uniformly continuous. Start with possible epsilon. And now we're going to consider the following open covering for y. So U prime is going to contain the set of all balls in y centered at an arbitrary point. So this is bigger y of radius, well, epsilon half because of technical stuff. You'll see this epsilon half in the moment. And here y is an arbitrary element of y. Right? So this is an open covering for y. Do you agree that's an open covering? Just take some ball around each point. Okay, so the problem is we only know X is compact, so we cannot do much about this guy. But we can use that F is continuous and pull this back to X. So since F is continuous, and I'm also using that if you do the preimage of the entire codomain, you will have the entire domain. The following you defined as the preimages of these guys so the preimages of these guys is an open covering for X. So what I'm saying here is, since Y is the union of these guys, and you take the preimage of all of them, you will get the entire X, and all of them will be open, all the preimages will be open because F is continuous. And now we can use that X is compact. So that open covering, we can just take finitely many of those to cover the entire space. Is the proof clear so far? Oh, I said I want to take a finite subcover of those things. That's not true. I just have my Lebesgue number lemma. I don't need to take any finite subcover. So let delta. So something I forgot to mention, by the way, and I also just erased the Lebesgue number theorem. The delta is called the Lebesgue number, a Lebesgue number for the covering. So it's not unique because you can take, if you have one, you can take any smaller one. So let delta be a Lebesgue number for this open cover for U prime, for U. And now I need to claim that this delta is going to work. So claim delta works. So what do I mean by works? I need to prove this, right? So I'll take any pair of points. So take any pair of points. Let's go with the blue version of the definition. So x1, x1, and x2 in X with distance from x1 to x2 smaller than delta. So I have 2 points, distance and most delta, or smaller than delta. In this case, the diameter of this 2-point set, x1, x2, so there's only, well, 3 distances, because between x1 and x1, x1 and x2, x2 and x2. So the diameter of this guy is smaller than delta. It's just the maximum between 0, 0, and delta, or that distance, which is more than delta. So this diameter is at most delta, which is a Lebesgue number for U, hence, by the Lebesgue theorem, by the Lebesgue number lemma, there exists something in U. We know how things in U look like. These are preimages. B center at Y, radius epsilon over 2. That contains the 2-point set. X1, X2 inside that preimage. Right? That's how things in U look like. And I know anything with the diameter smaller than delta is inside one of those. That's the big numbers level. Okay, and then we're pretty much done. Because if this 2-point set is inside that preimage, if that 2-point set is inside the preimage, the image of the 2-point set, that's going to be inside the ball, y epsilon over 2. Now you will see why I needed this epsilon over 2. Now I want to compute the distance from f of x1 to f of x2. But what's going on here is we know the entire f of that stuff is inside this ball, y epsilon over 2. So we don't really know where x1 and x2 live, but here's f of x1, here's f of x2. We want to compute the distance of these two guys, but the distance from each of them to y is at most epsilon half, so by the triangle inequality, the distance will be at most epsilon. So this we know, then by the triangle, we kind of know the other. Then f of x1 and f of x2 both live in this ball. And now we compute the distance in y from f of x1 to f of x2 is smaller than or equal to the distance from f of x1 to y plus the distance to f of x2, which is smaller than epsilon half plus epsilon half, which is epsilon. And that's exactly what we wanted. Any questions? Okay, let me hit stop then.